Welcome to FTIR Virtual Training. FTIR stands for Fourier Transform Infrared Spectroscopy. We will often abbreviate it just IR or FTIR. This section will cover some of the basics of how FTIR works and also some of the different experimental geometries that we have on our system. So how does the basic FTIR experiment work? We always compare the intensity of the infrared light that travels through a blank sample to the intensity that travels through your sample itself. And so these intensities I'm going to refer to as I and I naught. And for example, if your sample was a solid dissolved in a solvent, then your blank would just be that solvent. If your sample was a thin film on a substrate, then your blank would just be that substrate. So let's look at how we use those values of I and I naught to calculate a few things. Infrared spectra either report a transmission or an absorption. And so the transmission can be calculated simply by dividing I by I naught. And often this is recorded as a percent transmission. So that fraction is then multiplied by 100 to get the percent transmission. In this case, you will see peaks, transmission peaks, that go down on your graph. But very often we convert this into an absorbance. And so the equation for converting into absorbance is shown over here on the right. So the absorbance is just the negative log of 1 divided by the transmission. And if we substitute this I over I naught, we get this equation down here at the bottom. In this case, the absorbance then shows peaks that are up in direction on your graph. The absorbance can also be related to the concentration in your sample by the Beer-Lambert law. And that basically says that the absorption is equal to this molar absorptivity. That is a value that is different for every molecule. And that's multiplied by the path length or the thickness of your sample, the distance that the IR beam travels through the sample. And that's multiplied by then the concentration of that component in your sample. Many of you, especially if you've taken basic chemistry classes, have probably already seen this equation before. So another common geometry that I want to take a minute to explain is attenuated total reflectance. We often call this ATR. In this case, our infrared light travels down some kind of a crystal. This crystal has the shape of a trapezoid. And you can see what happens is that the infrared light, after it enters the crystal, it internally reflects off of these surfaces and travels down the entire length of the crystal until it exits out the other side. And at each one of these reflections, we get something that is termed an evanescent wave. So each one of these reflections has these evanescent waves that essentially penetrate beyond the crystal itself. And that usually penetrates a few hundred nanometers to a few microns past the edge of this crystal. And so if you put a sample in good contact with the crystal, you can start to probe it in an infrared experiment. And again, you would take a measurement with no sample in place. That would be your blank measurement or your reference measurement. And then you'd put a sample on and you'd collect the data. And then the software will often calculate either your transmission or your absorption, as we just discussed on the previous slide. We have a couple of accessories that allow us to do ATR experiments. And so I wanted you to see this. This particular geometry is a multi-bounce geometry. There are also ATR attachments that are just single bounce, that probe your sample in a single location, and we have both. So one of the first questions you have to ask yourself when you come to do FTIR spectroscopy is what geometry are you going to use? Now, our system has a number of different geometries that are possible. And the one that you're going to use is going to depend a lot on the form that your sample is in. But very briefly, our instrument kind of has two sides. This side over here on the left is what we often call the tensor. It is a basic FTIR spectrometer. And if you've done any FTIR spectroscopy in the past, you've likely used something that looks similar to this. But we can also send the infrared light from this system into a microscope, and that's a little bit different than what a lot of people have used. And so this system, you can't read it, but just on the right-hand side of the instrument, it says that this is a Hyperion microscope. So I may refer to this side as the Hyperion, this side as the tensor. So let's take a closer look at some of these. In the tensor, the very most basic experiment you can do is a transmission experiment. In that case, you put your sample in the middle of the sample compartment. The infrared light comes from the right, travels through your sample and onto the detector. So just as I showed you in the very beginning, you'd run one scan where you had a blank in place, and you'd run a second scan where your sample was in place, and the instrument would calculate transmission or absorption for you. Now, we also have this attachment here, which I've shown over here on the right, inside the sample compartment. This is an ATR geometry, just like I showed you before, where again, the infrared light comes in from the right-hand side. There are a series of mirrors inside this attachment that the light bounces off of in order to make it up to this yellow-colored crystal at the top. The infrared light then bounces down the length of that crystal before it comes out the other side, bounces off of another series of mirrors, and then makes it to the detector. So these are the two basic geometries we can use in the tensor. If we look at the Hyperion microscope, there's three geometries we can use. On the microscope, your sample is going to sit on the sample stage in all of these cases. And we can do a transmission experiment where we direct the light in through the bottom of the microscope, through the sample, and then collect it up through these objectives. We can also do a reflection experiment in which we bring the infrared light in from the top through one of the objectives. It bounces off of your sample and then comes back up again through that same objective to be collected. Finally, you can notice that this large microscope objective in the back is a little bit different than what we had before. This is a single bounce ATR objective for our Hyperion microscope. And again, the infrared light in this case comes from the top through that crystal, which we put in good contact with the sample. And then that evanescent wave will probe the sample, and we will collect the infrared light again through that crystal and up to the detector. So those are the 5 basic geometries that we can operate our system in. And you may be starting to think now about your particular sample and what's going to work best for your sample. Now let's talk a little bit about different types of samples and how we can run them and how we can prepare them for analysis. If your sample is a liquid, we need to talk about a few things. The first thing is that aqueous solutions are not very good for infrared spectroscopy. And the reason for this is that water absorbs strongly in the infrared. So, if your sample is actually something that's dissolved in water, maybe we can just drop cast it onto a substrate that's more appropriate. We'll talk about that in a minute. Another option, which I have not used very much, is to use some sodium chloride plates. And essentially you place a drop of your solution between these two very flat sodium chloride plates, and it creates just a very thin film of your solution or your liquid sample. And we do a simple transmission experiment through that. Now, this is obviously not good for aqueous solutions or really volatile materials. Aqueous solutions are going to dissolve your sodium chloride, and volatile materials may evaporate before we get a chance to measure them. Another option for liquids is the ATR attachment on the tensor. What we can do here is place a drop of liquid onto that zinc selenide yellow crystal, and then take data using that evanescent wave. Now, before you do this experiment, you need to make sure that you're going to be able to clean off that zinc selenide crystal and that it's not going to be damaged by your liquid. So check for chemical compatibility before doing this experiment. And then finally, if your sample is really something that is dissolved in a solvent, so it's a solution, then you may want to drop cast it on some kind of substrate where we can do a different kind of experiment. So one idea is to drop cast your sample onto a gold-coated silicon wafer. In that case, we can do a reflection experiment on the Hyperion microscope. The gold is very reflective in the infrared, and so it reflects a lot of the light back and allows us to do that experiment. Another potential substrate for this kind of experiment is double-side polished, undoped silicon wafers. They are transparent in the infrared. And so you could put a small drop of your sample onto that silicon wafer, let the solvent evaporate, and then do a transmission experiment either on the microscope or the tensor system. Now let's say your sample maybe is a powder instead. There's a couple ways we can look at powders. Powders can be pressed into KBR pellets. In this case, we mix a little bit of your sample with potassium bromide, and we mix it up very well. And then we press it into a pellet. The potassium bromide is transparent in the infrared, and so it is essentially just a way to hold our sample, a small amount of your powder sample in a transparent pellet so that we can do a transmission experiment. Typically, powders, again, can be dissolved or dispersed in solution and then drop cast, as we discussed above here, to do those types of experiments. So if you have a solid that's maybe either a freestanding film or just a bulk solid, there's a couple of things we can do. If the sample is thin enough, we can do a simple transmission experiment on either the tensor or the Hyperion microscope. But a lot of times samples are too thick and they absorb too much of the infrared light to give us any reasonable signal. In that case, ATR is a better option. If your sample is somewhat flexible, then the ATR attachment, the multi-bounce ATR attachment for the tensor is going to work best. So this is great for polymer samples that have a little bit of give to them. But if your sample is more rigid, harder sample, then the single bounce attachment on the Hyperion microscope is a better way to go. And if you have thin films on substrates, we need to think about that substrate a little bit. If the substrate is infrared transparent, you can do a transmission experiment, either on the tensor or the Hyperion. Some infrared transparent materials include the double-side polished undoped silicon that we talked about before, and salts like sodium chloride, and also zinc selenide and germanium. If the substrate is not IR transparent, then you may want to think about using the ATR attachment on the Hyperion microscope if the film is thick enough. So for example, we cannot yet see monolayers in this geometry. They're just too thin and our sampling depth is too great to see them in that particular geometry. So I hope you've learned a little bit about the system in general, how infrared spectroscopy works, and maybe are starting to have some ideas of what geometries you may run your samples on our system. If you have additional questions, feel free to contact me to discuss your particular samples in more detail, and we can identify a geometry that is going to work for you.